Good morning, everyone. In this lecture, we are going to discuss about power factor. What is your power factor and what is power factor correction? So, power factor is very important part of power system engineering or electrical engineering. Actually, the cost of electricity is dependent upon power factor. The quality of electricity is also dependent upon the power factor. So, it is a very important topic. In this lecture, we will discuss about the power factor and how a power factor can be controlled and how it affects our power generation process or power system engineering. So these are the learning objective. So learning objective that is define power factor, define unity, leading and lagging power factors, define power factor correction and unity power factor correction, calculate the inductor or capacitor value required to correct AC series parallel networks to the desired apparent power, compare currents, voltages and power in AC series parallel networks before and after power factor correction. So what is power factor? Power factor is tells us what portion of the apparent power is actually real power. So power factor is a ratio which is given by Fp is equal to cos theta, which is equal to P upon V RMS into I RMS. And power factor is equal to P upon S. So where P is your active power and which is divided by voltage into current. So you can also write P is equal to Pi cos theta on cos phi, where phi is your power factor angle and cos phi is your power factor. So power factor tells us what portion of the apparent power is real power. So power factor is expressed as a number between 0 to 1. So the minimum value of power factor is 0 and the maximum value is your 1. So you can say the power factor is as a percent from 0% to 100%. So the closer to 1.0 the power factor gets, the more resistive. The closer to 0.0 the power factor gets and more reactive. If the power factor is closer to 0, then the power factor is more reactive. So the power factor angle phi must be 0. The voltage and current, the angle between voltage and current must be 0 in the ideal case. So cos 0 becomes is equal to 1. Now power factor from the power triangle, it can be seen that Fp is equal to P by S or cos theta. So power factor angle is thus given theta is equal to cos inverse P by S. For a pure resistance, theta is equal to 0 degree. For a pure inductance, theta is equal to 90 degree. For a pure capacitance, theta is equal to minus 90. So if you draw, active reactive and apparent power in a vector diagram, so you will get this kind of vector diagram. On the x-axis, you can take real power. On y-axis, you can take reactive power, and the vector sum of these power is your apparent power. So from the equation, you can write Fp is equal to P by S is equal to cos theta. So power factor angle is thus given. Theta is equal to cos inverse P by X. So for a pure resistance, theta is equal to 0 degree. For a pure inductance, theta is equal to 90 degree. For a pure capacitance, theta is equal to minus 90. Now, power factor leading or lagging. So, how can you differentiate a power factor which is your leading or lagging? So, the term leading and lagging are defined in reference to the current through the load. So, if the current leads the voltage across the load, then the load has a leading power factor. If the current lags the voltage across the load, then the load has a lagging power factor. So, what is your leading and lagging power factor? You can see here. Fp is your power vector, which is equal to cos theta. Fp is equal to cos 40 minus 20, and Fp is equal to cos 16, that is equal to 0.5. So if you see that there is a motor, its voltage and current V is equal to 120 sine omega t plus 80 degree, and I is equal to 5 sine omega t plus 30 degree. So Fp is equal to cos theta, and Fp is equal to cos 80 degree minus 30 degree. And cos 50 degree is equal to 0.64 flat. So what is your unity power factor? Fp is equal to 1. Unity power factor implies that all of our loads operate on a single power Fp is equal to 1, then theta is equal to 0 degree. It could be also be said that the load looks purely resistive. So in resistive load, there is a voltage waveform which is same with current, and there is no angle between voltage and current. So it could be also that the load looks purely resistive, and the load current and voltage are in phase. Lagging power factor theta is always greater than 0 degree. So the load current lags over load voltage implies that the load looks inductive. Now, leading power factor theta is always less than 0. So the load current leads load voltage implies that the load looks capacitive. Sample problems. First, we will discuss about some examples by which you will be able to understand what is your power. So determine P, Q, S, and the FP for the circuit. So draw the power triangle. Is it leading or lagging power factor? Is the circuit inductive or capacitive? So you can see that this is the solution by which you can easily understand that what is your power factor. To two parts. This is your Kr92 nucleus and this is your Ba141 nucleus. It releases some energy in the form of your neutrons. Okay, so it is this energy is utilized to create or generate the power. Okay, and this energy can be utilized as a fuel. So here we can discuss the nuclear fission in detail. That you can see over here, it is a process of splitting up of nucleus of fissionable material like uranium into two or more fragments with release of enormous amount of energy. So the nucleus of uranium 235 is bombarded with high energy neutrons. Okay, so uranium 235 is bombarded with high energy neutrons. Okay, then it is divided into two parts, Ba141 and Kr92. Then it is releasing 2.5 neutrons and 200 mega electric volt energy, which is very high. Okay, so one uranium when is bombarded with a neutron, high energy neutron, it released 200 mega electronic volt energy, and the unit of this energy is always denoted by in electron volt, because there are n number of electrons are releasing. So the neutron produced are very fast and can be made to fission other nuclei of uranium 235. So setting up a chain reaction, out of 2.5 neutrons released, one neutron is used to sustain the chain reaction. So 1 electrovolt is is equal to 1.6 into 10 to the power minus 19 joule, and 1 mega electrovolt is equal to 10 to the power 6 electron volt. Okay, so one electrovolt has this much of energy, which is represented in joule, which is 1.6 into 10 to the power minus 19. So the neutrons produced are very fast and can be made to fission other nuclei of uranium 235. So the setting up a chain reaction, out of 2.5 neutrons released, one neutron is used to sustain the chain reaction. Now we come to the nuclear fission. So you can see over here that uranium 235 splits into two fragments, barium 141 and K92, of approximately equal size. You can see over here that when it is bombarded with a slow neutron, that uranium 235 is divided into barium and Kr, and this is your fission fragment. 0.6 fast neutron is released, one fast neutron is released, then 0.9 fast neutron over here released, fission fragment, heat, and gamma radiations. So these are the components, or these are the uh, basic thing which are releasing when a slow neutron bombard with uranium 235. Then moderator, this is the moderator which increases its reaction, or you can see over here that this slow neutron again collapse with the uranium, so it again increase some of energy. So uranium 235 split into two fragments, Ba141 and K92, which are approximately equal in size. So about 2.5 neutrons are released. One neutron is used to sustain the chain reaction, and 0.9 neutrons is absorbed by uranium 238 and become Pu239. So the remaining 0.6 neutron escape from the reactor. Okay, uh, 0.6 neutron which is escapes from the reactor, and the neutrons produced move at a very high velocity, which is 1.5 into 10 to the power 7 milli per second, and fission other nucleus of uranium 235. So the fission process and release of neutron takes place continuously throughout the remaining material. A large amount of energy, 200 million electron volt, is produced, which is very large amount of energy, which is very difficult to handle. So moderator are provided to slow down the neutron from the high velocities, but not to absorb them. Actually, some of the neutrons are absorbed by the reactor, but we use moderator, which slow down its reaction, but it will not absorb the neutrons like your reactor. Okay, so this is your nuclear fission where you are taking one uranium and yeah, it is collapsing with neutron, and then it is divided into two parts and releasing a large amount of energy and neutrons. Then this these barium and uranium again divided into two parts, which is split into two U238 and becomes Pu239. So the chain is continuous mode, and we use moderator. You can see over here, which is going to slow down the chain reaction of this uranium, but it is not going to absorb any kind of neutrons over here. Okay, so this is your nuclear fission. Now, basic principle of nuclear atomic power plant. So one is your core. So you can see over here, this is your reactor. Okay, so here the nuclear fission process takes place. This is your reactor where nuclear fission process takes place. This is your boron control rod, graphite moderator, fuel element change channel, concentrator, steel. It is made by steel. Reactor core, hot gases and heat exchanger. This is your cold gas. Okay, so what is moderator, which is very important? Moderator, this reduces the speed of fast moving neutrons. Most moderators are graphite, water, or heavy water. So, in the form of moderator, we can use graphite, water, or heavy water. Okay. So, moderator is basically used to reduce the speed of fast moving neutrons, and in the form of moderator, we can use graphite, water, or heavy water. So principal, or you can say main parts of a nuclear reactor is control rods. So what is the use of control rods? Because as the name is showing that control, and rods mean a symbol of rod. So it is controlling something. So we can see over here that these are your control rods, and in which you can see that this is neutron, this is your fuel assembly, and this is your reaction. When reactor is off, there is no reaction. When reaction is on, that you can see over here that it gets heated. There are n number of neutrons which is producing over here. So control rods limit the number of fuel atoms, okay, that can split. So they are made of boron and cadmium, which absorb neutrons. Okay. So controlling rods are absorbing neutrons, but moderator is not absorbing neutrons. It is slowing down the reaction. Okay. It is slowing down the reaction. So this is the difference between moderator and control rods. Moderator is going to slowing down the reaction, chain reaction, and control rods are controlling your number of fuel atoms that can split. Okay, so as a moderator we were using graphite, water, and hard water, but in controlling, as a controlling rods, we are using boron and cadmium. Okay, now the third part of this reactor is your coolant, because you are you know that very high energy is generated through this chain reaction. So at a very large amount of heat is generated. So to cool down this heat or this process or this reactor, we are using cool water. So they carry the intense heat generated. Water is used as a coolant, and some reactors use liquid sodium as a coolant. Okay, so you can use water or liquid sodium to cool the reactor. Next is your fuel. As a fuel, we are using over here uranium 235 isotope. So, fuel is your uranium 235. In thermal power plant, the fuel is your coal. Okay. Now, radiation shield, which is the very important part of this nuclear power plant, because when you can see over here that yes, you can see over here that there are some uh, you know gamma and beta rays are radiations are coming out of this chain reaction, which is very harmful for human body. Okay, it can produce very a number of diseases in your human body. So radiation shield is very important. It must not be touched to the human body and the workers who are working in nuclear power plant. So radiation shield to protect the people working from radiation and radiation fragment, we use thermal shielding. So this is your this is our main part of nuclear power plant. Okay, now the chain reaction, uncontrolled nuclear reaction, that was your controlled nuclear reaction, and this is your uncontrolled nuclear reaction. So we already know about the nuclear bomb, which was thrown on Japan in the Second World War. So that was the uncontrolled nuclear reaction. So in uncontrolled nuclear reaction, you can't control the chain reaction, and even you can't slowing down the chain reaction. So the chain reaction, when if you are not using any kind of moderator and you are not able to slowing down the chain reaction is not slowing down, the rate of fission increases rapidly. It will increases rapidly, and a huge amount of energy will be released very quickly. So it comes into the form of nuclear bomb, which is very harmful. Okay, so the chain reaction must be controlled, and it can be controlled by using the moderator, which is going to slowing down the reaction, which is very useful in which is the very important part of nuclear reactor, which is your moderator. Okay, so there are two type of reaction. One is your controlled reaction and another one is your uncontrolled reaction. If your chain reaction is controlled, then you can the energy which you are getting, you can easily utilize that energy. But if your reaction is get uncontrolled, then you can't use this energy and it comes into the form of nuclear bomb. Okay, which is very harmful. So these are the pictures of nuclear power plant. So rate of fission is controlled by artificial means to generate electricity. Okay. So the Bay nuclear power, this is the picture of nuclear power station. Now we comes to the hmm. So we comes to the different types of nuclear power plant, which is divided into main two parts. One is your pressurized water reactor plant, and another one is your boiling water reactor plant. In short, you can represent by it PWR, which is your pressurized water reactor plant, and BWR, which is your boiling water reactor plant. Okay, so what is your pressurized water reactor plant? So heat is produced in the reactor due to nuclear fission, and this is a chain reaction. Okay. In pressurized water reactor plant, you can see over here that there is a concrete shielding. Okay. This is your reactor core. This is your fuel rods. Okay, fuel, you are using uranium by which this fuel is supplying through the rods. This is your thermal shielding. Okay, thermal shielding which is used to for harmful radiation which is producing after the nuclear reaction. This is your hot coolant to cool the heat, pressure equalizer, steam and steam generator. So the heat energy uh, which is producing after this nuclear reaction. That heat energy is transferred over here, which generate the steam. Okay, and this steam is supplied to the steam turbine, which convert it into the mechanical energy. So the turbine start rotates, and this turbine is directly connected to the generator. So when turbine rotates, the mechanical energy of this is converted into the electrical energy, and some exhausted steam is coming over here, which is not utilized over here. So this exhausted steam can be used in cooling water, and it is condensed again, that in again comes into the water form. Then it is feed into the steam generation by using the feed pump. This water again goes into over here, and by using this hot coolant, it is converted into the steam, and this steam is going into the again going into the steam turbine. So this is your pressurized water reactor. So the steam generator is a heat exchanger where the heat from the coolant is uh, transferred on the water that circulates through the steam generator. As the water passes through the steam generator, it gets converted into steam. So the steam produced in the steam generator is sent to the turbine, and turbine blades start to rotate. So turbine shaft is coupled to the generator, and the mechanical energy is converted into the electrical energy, and electrical energy is produced. After the steam performing the work on the turbine blades by expansion, it comes out of the turbine as wet steam. This is converted back into water by circulating. So the feed pumps back the condensed water into the steam generator. So this is all about your pressurized water reactor. Okay. Now, because why this is called pressurized water reactor, that the water is coming over here, and the hot heat is through the pressure is thrown to this. It is fed into the steam generator. So this is your schematic diagram of a nuclear with PVR. Okay. So this is your reactor pressure vessel, fuel rods, and these are your controlling rods. This is your reactor core, and this is your hot water, because chain reaction is going into the this reactor. So the energy which is producing by this, which is supply into the this water, and water gets heated. Okay, so this water gets heated, then it converted into the steam, and this steam is transferred to the turbine, and this turbine is connected to the generator, which is generate the electricity. And this is your exhausted steam, which is coming into the condenser. Again, it is converting into the water, and then water is again going into the steam generator, and you are again getting water to heat. Okay, so this is all about, this is called your primary loop, where chain reaction is happening, and this is your second loop, secondary loop, where your electricity is generated. Okay, so this is your schematic diagram of nuclear power plant with PWR. Now, so this is your fuel rods. Okay, which is very important. Just a minute. Yeah. So this is your fuel rods. They contain the nuclear fuel uranium U-35. They are surrounded by a moderator to slow down the neutrons released. Okay. So they control the rate of reaction by moving in and out of the reactor. Okay. If you want to slow down uh, if you want to slow down the reaction, that you can, then you can see that They control the rate of reaction by moving in and out of the reactor. So moving in rate of reaction, moving out rate of reaction, all are moved in, the reactor is shut down. Okay. So by using these rods, you can easily understand how moderator is controlling the reaction. If all rods are getting down or rods are getting inserted, then the reactor is getting shut down. So there will be no chain reaction. So by moving up and down, the chain reaction can be controlled. And they are made of boron or cadmium that can absorb neutrons. So the steam drives a turbine which turns the generator, and electricity is produced by the generator. Okay. Now, two separate water systems are used to avoid radioactive substances to reach the turbine. That's why we are using two separate water systems. Okay. This is your two separate water system. Fine. So, are used to avoid radioactive substances to the turbine. So another part of this is your boiling water reactor. Okay. So we have studied about PWR. Now this is your boiling water reactor. So what is your boiling water reactor? So boiling water reactor, the water is circulated through the reactor where it converts to water steam mixture. Okay. So it is already known that in thermal power plant, what we were doing, we were doing, we were converting water into the steam. So in this reaction, in this boiling water reactor, the water is converted into the steam. So water is circulated through the reactor where it converts to water steam mixture, and the steam gets collected above the steam separator. So this steam is expended in the turbine, which turns the turbine shaft. Okay. So the expanded steam coming out of the turbine is condensed and is pumped back as fed. So the water is circulated through the reactor where it converts to water steam mixture, and the steam gets collected above the steam separator. So this steam is expended in the turbine, which turns the turbine shaft. So the expended steam coming out of the turbine is condensed and is pumped back as feed water by the feed water pump into the reactor core. So also the downcoming recirculation water from the steam separator is fed back to the reactor core. So this is a steam power plant, means any plant that uses steam to produce electricity. For example, thermal and nuclear power plants. In both we are using steam. In both we are using steam to generate the electricity. But there is a big difference between nuclear power plant and thermal power plant is the fuel. Because in thermal power plant we were using coal as a fuel, but in nuclear power plant we are using uranium as a fuel. So advantages of nuclear power plant. So space required is less when compared with other power plants, and nuclear power plant is the only source which can meet the increasing demand of electricity at a reasonable cost. A nuclear power plant uses much less fuel than a fossil fuel plant, means in nuclear power plant you require very less amount of fuel. Okay. But in thermal power plant there we have already studied that the large amount of fuel was required to generate the electricity. So 1 metric ton of uranium fuel is equal to 3 million metric ton of coal, is equal to 12 million barrels of oil, which is very large amount of fuel in thermal power plant. So space is less, fuel is less, and reasonable cost of electricity. Now, the main disadvantages of nuclear power plant, which is not very much popular in India. So, radioactive wastage must be disposed carefully because which is very harmful for human body. Okay, so otherwise it will adversely affect the health of workers and the environment as a whole. So, maintenance cost of plant is very high. Okay, so this is the main disadvantages of nuclear power plant. Now, nuclear waste. So they are highly radioactive. Many of them have very long half lives. So radioactive waste must be stored carefully because it can damage the human body. Low level radioactive wastage, uh, cooling water pipes, radiation suits, etc., stored in storage facilities. Radioactivity will fall to a safe level after 10 to 50 years. So before 10 to 15 years, you can't even go over there, you know. So this is the main disadvantage of nuclear power plant. Now, high level radioactive waste used nuclear fuel and highly radioactive embedded in concrete and stored deep underground for several thousand years. Okay. So this is the main disadvantages of nuclear power plant. So we have studied about nuclear fission. Now this is nuclear fusion. So nuclear fusion, it is light nuclei fused together to form a heavier nucleus. Okay. In the nuclear fission, what we were doing, we were taking an atom and a nucleus, and the nucleus and atom both were colliding each other, and they were producing more uranium and more nucleus, and the reaction will remain continuous. Now, in nuclear fusion, light nuclei fuse together to form the heavier light nuclei fuse together to form a heavier nucleus. So you can see over here that it is divided deuterium, helium, neutron, and tritium, and energy is released. Nuclear fusion. Nuclear fusion, light nuclei fuse together to form a heavier nucleus. Deuterium nucleus, you can see over here that when deuterium and titanium nucleus collide to each other, then this will release the energy, and this is the equation where you can see that the energy which is releasing your proton, and this is showing your neutron. So if you have any query, you can ask from me, and the reference of this lecture is your NPTEL and Generation of Electrical Power, which is written by B.R. Gupta. Okay, you can get the study material from NPTEL, and you can go through this book where nuclear power plant is well explained in B.R. Gupta. Okay, so now we can summarize this nuclear power plant. That nuclear power plant is used to generate the electricity, where as a fuel we are using uranium, and the chain reaction is divided into two parts. One is your nuclear fission and another one is your nuclear fusion. Okay, and there are more important thing which is used in nuclear reactor, which is your moderator, which is used to get the slowing down the chain reaction of the chain reaction of the uranium. Okay, so there are different kind of equipments which we were using in nuclear power plant. In nuclear power plant, the energy which is releasing after the nuclear fission, which is used to heat up the water, and then water is converted into the steam, and that steam is thrown or fed to the turbine. So it rotates the blades of the turbine. So the energy of steam is converted into the mechanical energy through the turbine, and this mechanical energy is again converted into the electrical energy by using the generator. So this is all about your uh, nuclear power plant. Now we come to the some MCQs, which is based on this lecture. So it would help you to understand the this lecture more. So our first question is, the efficiency of a nuclear power plant in comparison to a conventional thermal power plant is. So the efficiency of a nuclear power plant as compared to conventional thermal power plant is less. Okay, because it requires more safety as compared to thermal power plant. Okay. Second question is, isotopes of same elements have same atomic number and different masses, same chemical properties but different atomic numbers. uh, you have seen that we were using uranium 235 and 238, which has same chemical properties, but they have different atomic numbers. So the answer for this question is your B. So third question is, atomic number of an element in the periodic table represents the number of protons in the nucleus, electrons in the nucleus, neutrons in the nucleus, and electrons in the atom, neutrons in the atom. So everyone knows that we have studied this is in school. The atomic number is always represented by the number of protons. So atomic number of an element in the periodic table represent the protons in the nucleus. Another question is, the mass number of a substance represent the sum of total number of. So already we have studied in our low class protons and neutrons in an atom, protons and electrons in an atom, neutrons and electrons in an atom. D part is your protons and neutrons in a nucleus, and last part is your protons and electrons in a nucleus. So protons and neutrons in a nucleus is always represent the mass number of a substance, right? Now we come to the another question. So which is not identical for an atom and an isotope? So one option is your mass number, atomic number, chemical properties, position in periodic table, all of the above. So mass number is not identical for an atom and an isotope. Okay. Now another question. Amongst the following, the fissionable material are uranium 233 and Pu 239, uranium 231 and Pu 233, uranium 235 and Pu 235, uranium 238 and Pu 239, uranium 243 and Pu 235. So we have already seen in our slides that uranium 233 and Pu 239 is the fissionable materials. Next is your a nuclear unit becoming critical means. Why nuclear unit is becoming critical? Because it is generating power to rated capacity. It is capable of generating much more than rated capacity. There is danger of nuclear spread. Chain reaction that causes atomic splitting of the fuel nuclei has been established. it generates no heat. So, you know, for in nuclear power plant, when chain reaction occurs, there is so much heat is generated, and there is a danger of nuclear spread. Okay, so more critical part of this, that there is a danger of nuclear spread. Okay, now another question. Moderator in nuclear plant is used Moderator in nuclear plant is used. One is your reduce temperature, second one is your extract heat from nuclear reaction, third one is your control the reaction, fourth is your cause collision with the fast moving neutrons to reduce their speed, and last one is your moderate the radioactive pollution. So we have already discussed that moderator is always used to slowing down the reaction of nuclear. Okay, so D is the right answer for that. That a moderator cause collision with the fast moving neutrons to reduce their speed. Right, now another question, we come to the another question, which is the most commonly used moderator in nuclear plant is: one is your heavy water, B is your concrete and bricks, third is your graphite and concrete, D is your deuterium, E is your graphite. So everyone knows that graphite is very popular, which is used as a moderator in nuclear power plants. So E is the right answer for that. Now another question. The nuclear energy is measured as, when we saw the chain reaction, you saw that the nuclear energy which released in number of neutrons in the terms of neutron. So always it is represented by the options are given. First we have to see the options. What are the options are given? One is your mega electronic volt, B is your megatonnic volt, C is your megatonnic volt, D is your megatonnic volt, and E is your megatonnic volt. So the option for this question is your mega electronic volt. Now another one is your the total energy released in fission of U is 5 mega electronic volt, 10 mega electronic volt, 199 mega electron volt, 168 mega electron volt, and 11 mega electron volt. So it is approximate 199 mega electron volt. So this is all about your nuclear power plant. So we have seen that how it is different from your conventional, which is your thermal power plant, and what are the basic difference between thermal power and nuclear power plant, and what are the equipments we are using in nuclear power plant, and another one is your what are the advantages and disadvantages of the nuclear power plant, and we have done the different two types of nuclear power plant. Okay, and the some objective which is based on this lecture. So this lecture is done. If you have any problem, you can ask in the next lecture. Thank you.